The Evolution of Functional Programming Paradigms, a comprehensive exploration. Functional programming is an intriguing paradigm that has captivated the minds of developers worldwide for several decades now. It's a conceptual approach to writing computer programs, emphasizing immutability and first-class functions as its core principles. This unique perspective on coding presents programmers with powerful tools to tackle complex problems in various fields, including technology, science, finance, and more. The roots of functional programming can be traced back to the pioneering work done by Haskell Curry in the 1930s with combinatory logic. However, it wasn't until the late 20th century that its potential was fully realized, primarily through the development of Lisp, a programming language specifically designed for functional programming. The introduction of Scheme and other dialects further established functional programming as an essential aspect of computer science research and practice. Over time, several languages have embraced functional programming paradigms to varying extents. One prominent example is Haskell, which has been regarded as the quintessential pure functional language since its inception in 1990 by Robin Milner's team at Edinburgh University. Alongside Lisp-derived languages such as Clojure and Scala, a hybrid of functional programming with object-oriented features, Haskell continues to push the boundaries of what is possible within this paradigm, constantly evolving and expanding its capabilities in response to new challenges faced by developers worldwide. The appeal of functional programming lies not only in its theoretical foundations, but also in how it translates into practical applications across multiple domains, from software development to scientific modeling, finance analysis, and even artificial intelligence. However, this paradigm's journey hasn't been without its critics. Some developers have expressed reservations about functional programming due to perceived constraints on performance and readability, particularly when dealing with complex systems. In recent years, the emergence of multi-paradigm languages like Scala has helped bridge these gaps by offering a more seamless transition for traditional programmers while providing them access to powerful, functional constructs. This approach demonstrates that it's possible to harness the benefits of multiple programming styles without sacrificing performance or code maintainability. At its core, functional programming is characterized by two key principles: immutability and pure functions. Immutability refers to a fundamental property where data structures are not changed once created. Instead, new versions are created with any desired modifications. This approach eliminates the need for complex state management and debugging associated with mutable variables, factors that have long plagued traditional programming styles such as procedural or object-oriented languages. Pure functions represent another cornerstone of functional programming. A function is said to be pure if it produces consistent outputs given identical inputs, irrespective of the surrounding environment. This principle ensures predictable behavior and facilitates parallel computation, since there are no side effects that could cause race conditions or other issues when running multiple instances simultaneously. These principles have led to several benefits within functional programming paradigms. Among them is easier reasoning about code, which simplifies debugging processes and promotes cleaner software design. Additionally, immutability can lead to improved performance in some scenarios since it eliminates the need for data locking and synchronization mechanisms, problems commonly encountered when dealing with mutable state across multiple threads or processes. Moreover, functional programming has found its way into modern AI techniques, like machine learning and deep learning, where pure functions are used to build sophisticated models while maintaining the clarity of code structure. Functional programming's emphasis on declarative statements helps researchers articulate complex mathematical operations concisely, making it an ideal fit for AI applications that require high precision and accuracy in model construction. Nevertheless, despite these undeniable advantages, functional programming paradigms are not without their drawbacks. Critics argue that its strict adherence to immutability may lead to increased memory consumption, as it often requires creating new objects or data structures rather than modifying existing ones in place. Furthermore, the emphasis on pure functions can also present challenges when working with real-world systems where side effects are unavoidable. Such instances require careful consideration and application of design patterns that accommodate these necessary changes, while still preserving some semblance of functional programming principles. As we venture deeper into this fascinating world, it becomes apparent that the evolution of functional programming paradigms has been a product of continuous refinement and adaptation to real-world demands. While its roots can be traced back decades ago, modern advancements in both language design and algorithmic thinking have pushed the boundaries of what is possible within this unique framework. In conclusion, functional programming represents an essential paradigm that has made significant strides over the years in addressing complex problems across diverse domains. Its emphasis on immutability, pure functions, declarative syntax, and modular code structure offers programmers a powerful toolkit for tackling challenges with clarity, efficiency, and elegance. As functional programming continues to evolve alongside emerging technologies like AI, data science, cloud computing, and distributed systems, its potential to transform the way we interact with our digital world remains unmatched. Throughout this exploration of functional programming paradigms, it has been my pleasure to delve into the rich history, current state-of-the-art applications, and ongoing challenges associated with this compelling approach. I firmly believe that as developers continue their journey in search of novel solutions for increasingly intricate problems, both within our technological society and beyond, functional programming will undoubtedly remain a cornerstone paradigm, deserving of further research, experimentation, and innovation. In this ever-evolving landscape, it's vital to embrace the dynamic nature of functional programming, while also recognizing its strengths, weaknesses, and unique position within the broader spectrum of coding styles. By doing so, we can continue to explore new possibilities, inspire fresh perspectives, and ultimately shape a future where our digital tools better serve humanity's needs, all through the power and potential of functional programming paradigms.